In this video, we're going to look at the concept of hybridization. Hybridization is a theory that looks at combining atomic orbitals, mixing them to get hybrid atomic orbitals that are used in bonding. So let's use hybridization theory and look at how we can explain the bonding in the simplest compound of carbon, methane, CH4. So what do we know about methane? We know that all of the carbon-hydrogen bonds are equivalent. They are the same length, and all of these bond angles are identical. They're 109.5 degrees. So let's come up with a theory that explains this bonding pattern of methane. Carbon having 4 bonds, all identical, leading to same bond lengths and same bond angles. So if we look at the electron configuration, which is going to be most important for the valence electron configuration. So let's look at the 2s and the 2p orbitals here. Carbon has 4 valence electrons, so our model would look something like this, our electron configuration. And based on this configuration, we have 2 electrons here that are unpaired that could be used for bonding. And so by this simple drawing here, we would get a structure of carbon and hydrogen, the simplest carbon compound of CH2 here with a lone pair. And in fact, we don't see this compound existing. This is the simplest compound of carbon. So we have to change our model here to explain our experimental evidence. So let's adjust something here. Let's say that we have our 2s and our 2p, and we excite one of these electrons from the s to the p. This energy is not that big in the scheme of things, so it is possible to promote one of those electrons to a p orbital. Now we have this case where there are 4 unpaired electrons that could make 4 bonds with carbon. So now we have to think about how those 4 bonds would orient themselves. So if we have my s orbital, which is spherical, and then I have my 3p orbitals. These are dumbbell shaped, and they are 90 degrees from one another. And then the most difficult one to draw here is the one coming in and out of the board. So that's coming out, and this is going back in, the dashed one. So then when I think about placing my atoms on these orbitals to make those bonds, I would have a hydrogen atom overlapping with a p orbital, another hydrogen atom overlapping with p orbital, and then another hydrogen atom overlapping with p orbital. And based on the bond angles of these atomic orbitals, what would the bond angles have to be between these hydrogen atoms? Well, they'd have to be 90 degrees because the p orbitals are all perpendicular to one another at 90-degree angles. And then that 4th bond would have to be the overlap of the 2s with the 1s of hydrogen. And where does that go? The s orbital is spherical, so we could pop it on here anywhere, and we'd imagine looking at one methane and another methane that they could be in different places and have different angles from molecule to molecule. But all methane molecules have this structure, all have the same bond length and bond angles. And this model is still not sufficient to explain the bonding in methane. We have 2 different kinds of bonds, the 1s and 2p orbital overlap. There are 3 of those, and then the 2s, 1s orbital overlap here. And the bond angles are all not identical. So again, it's not quite satisfactory. So let's try this again. Let's look at mixing these atomic orbitals. Okay, so we're starting from our excited state where we have this electron promoted to the 2p shell. So now we're going to mix all of these together. We're going to hybridize them, in other words. So we put 4 orbitals into a blender. If we put 4 orbitals in, we must get 4 orbitals out. It's the same idea as if I put 4 glasses of juice in, I'm going to get the equivalent of 4 glasses of juice out, no matter how many different kinds I put in. So I'm going to fill this according to the rules, and because they're all the same energy, I fill them in order as such. So then what do we call this hybridized orbital? Well, it was 1 part s and 3 parts p, so we call this the sp3 3 hybridized orbitals. Okay, so it's the idea if we're going to make a cranberry orange drink and we put 3 glasses of cranberry juice in the blender and 1 glass of orange juice in the blender, we put 4 glasses of juice in, we get 4 outs, and it's a hybrid, it's a mix of cranberry and orange juice. This is a mix of the s and the p orbitals, and we denote the proportions that they're mixed as sp3, 1 part s, 3 parts p. Now let's consider the shape of the sp3 orbital. The s orbital is spherical, and the p orbitals, we're going to take 3 of those dumbbell-shaped orbitals and mix that all together. So we might expect that the sp3 orbital will look more like the p orbital, and in fact it does. It's a little bit of a distorted p orbital, with one side is larger than the other. And so this is a way that we can explain the bonding in methane. These 4 equivalent orbitals will be as far away from one another as possible to form the 4 identical bonds to hydrogen and explain the bonding pattern observed in that molecule. Sp3 hybrid orbitals will be used in bonding for most compounds having 4 domains. So if we think about not just methane, but things like ammonia, NH3 with a lone pair, and water, OH2O, those all have 4 electron domains, so we need 4 hybrid orbitals to form those bonds about the central atom. Thanks for watching.